Welcome to Study Loop.
In this exercise, we have a more general transmission probability, T, that's given here on the first line, by 1 plus u0 times the hyperbolic sine of KL squared divided by 4e u0 minus e to the minus 1, where u0 is the height of the potential barrier, e is the energy of the particle, L is the length of the potential barrier, and K is equal to the square root of 2m times u0 minus e divided by h bar. In question A, we have to show that when KL is much greater than 1, the transmission probability reduces to the formula that we had before in the book. That's the second equation here on the screen. T is equal to 16e divided by u0 times 1 minus e divided by u0 times e to the minus 2 KL. So basically, I'm going to take the first equation, and then I'm going to impose that KL is much greater than 1. First, notice that the hyperbolic sine of KL is equal to 1/2 of e to the KL minus e to the minus KL. And when KL is much greater than 1, e to the minus KL tends to 0, so this is approximately 1/2 of e to the KL. So you can go back to the transmission, which is 1 plus u0 times the sine, the hyperbolic sine of KL, which, as I just showed, is approximately e to the KL divided by 2 squared divided by 16 e u0 minus e. So this is, I'm sorry, not 16, this should be 4. So this is equal to 1 plus u0 squared e to the 2 KL divided by 16 e u0 minus e to the minus 1. Now notice that if KL is much greater than 1, then we have that the exponential of 2KL is much greater than 1. So we can disregard the first term, that is this 1 here. I'm simply going to disregard it. So T is approximately equal to u0 squared e to the 2 KL divided by 16e u0 minus e to the minus 1, and this is e to the minus 2 KL times 16e u0 minus e divided by u0 squared. So this is equal to 16e divided by u0 times 1 minus e divided by u0 times e to the minus 2 KL. Okay, so this is exactly the expression that we had in the book for KL much greater than 1. Then we have to explain why we imposing that KL is much greater than 1 implies that either the barrier is relatively wide or that the energy E of the particle is small compared with U0. Well, notice that for KL to be much greater than 1, either L is much greater than 1 over K, okay? In which case L is relatively wide. I'm sorry, the barrier is wide, so L is large, or K is much greater than 1 over L. Now notice that K is the square root of 2m times u0 divided minus e. So for this to be very large, u0 must be large compared to e. Okay, so for that reason, e is relatively small compared to u0. Finally, in question C, we have to show that when the kinetic energy E approaches u0, then the transmission probability T approaches 1 plus k L over 2 squared to the minus 1. Okay, and we can use that when x is much smaller than 1, the hyperbolic sine of x is approximately x. So I'm going to start by rewriting here the equation for the transmission probability. So I have 1 plus u0 times sine the hyperbolic sine of kl divided by 4e u0 minus e here squared minus 1. So basically, notice that e0 approaches u. In that case, k approaches 0 since k is equal to the square root of 2m times u minus e divided by h bar. And in this case, the hyperbolic sine of kl approaches kl, so we have 1 plus u0 times kl squared divided by 4e u0 minus e to the minus 1. So t is equal to 1 plus u0 squared plus k squared, which is equal to 2m times u0 minus e divided by h bar squared times L squared divided by 4e times u0 minus e. So notice that the u0 minus e cancel, and I'm going to substitute u0 for e since e approaches u0. So one of these here cancel. So t, there's a minus 1 here. So t is equal to 1 plus 2me L squared divided by 4 h bar squared to the minus 1. So t is equal to 1 plus the square root of 2me divided by h bar times L divided by 2 squared to the minus 1. And now defining k to be equal to the square root of 2me divided by h bar, you get that t is equal to 1 plus kl over 2 squared to the minus 1, which concludes our exercise.